Hey folks, in this video we're going to take a look at the pre-order and post-order traces of exploring a DFS. Our claim, of course, that we want to investigate is that the reverse post-order of a graph is a topological sort of a graph. So that's what we're going to try to get to. So let's take a look. Up top I have a graph. So this is my sample graph G, and this sample graph G I want to run DFS on. And I've actually already kind of done it, and I've worked it out in the slides. So we start at 3, right, and then we go explore. So basically we start at 3, right, and then we go to 0. Then we have to backtrack, go to 4, right, we'll go to number 1, right, and then from 1 we'll go to 2, then we'll backtrack to 1, then we'll go to 4. Okay, so it's kind of like we're moving through it right in a certain way. I have kind of the trace of it shown on the left-hand side, so you can see these are the recursive calls that are made. Then over here, right, this is basically that DFS tree that will be generated, right? So these are the specific edges that were taken when we did the actual DFS algorithm on it, okay? So those two things there, right, are basically my trace. So let's see, what does this look like? Let's say I'm trying to do the pre-order traversal. That means basically that I write down nodes before I act on them. So the pre-order for this traversal, right, well, normally I start at 3, right, so I basically would write down 3, right? Then I go, from 3 I basically go up to 1, go up to 0. 0, right, I would write down, and I don't have anything else to do, so then I backtrack to 3. From 3, I would go to 1, right, and I would write it down. And then from 1, right, I have different options. I could go to 0, I could go to 2, I could go to 1. Well, 0 isn't useful to me, right, it's already marked, so I'm not going to bother with it. Next one I look at is 2, so I go explore 2, right, so I'd write that down pre-order, right, it means that as I explore something for the first time, I write it down. So I see 2, and then I'm at 2, I'm stuck, I don't have anything to do, I go back to 1. Well, 1 has one more thing to explore out of it, which is 4. So then I go down and explore 4. Okay, so I explore 4, and then I'd write that down. So yeah, that's how I get my ordering here, right? My 0, so 3, 0, 1, 2, 4 is my pre-order traversal, right? If I do DFS on this graph here, right? And you can kind of see it follows a lot, right, from this overall recursive trace, right? Because just like the first time I see anything, I'm going to write it down. Okay, so it's pretty easy to figure out. Now what we can look at doing is the post order. Okay, so the post order looks like what? The post order, right, means we write it down after we're done with it. Okay, so initially I start at 3. I can't write it down initially because I'm not done with 3 yet, right? Only once I'm done with a node do I write it down in the post order. So first one I see, right, is 3. So I go up there again. First one I see is 0. That's the first one I see again. 0, there's nowhere else to go, so I'm done with it. So I'm actually going to write it down first. Then I backtrack to 3. But 3, I'm not done with it. I still need to explore 1 and 4, so I can't write it down yet. So I'm at 3, I go look at 1. 1 has those choices again. It ignores 0 because, hey, it's already been explored. And it goes looks at 2. So it looks at 2. 2 doesn't have anybody come out of it, so I don't have anything to do. I'm done with it, so I can write it down. So basically, I went from 3 to 1, then from 1 to 2, and then I finished that, right? I'm going to go back to 1. So I'm at 1, right? I have just one more choice, which is 4. So I go look at 4. 4 is only connected to 2. 2 is already marked, so I don't need to go explore 2 again. So hey, I'm done with 4, so I can write down 4, right? Again, I'm writing things down after I'm done with them. So I went from 1 to 4, right? And then I undo it, go back to 1. Well, hey, now I'm done at 1, right? I looked at 0, didn't do anything because it was already marked. Then I dealt with 2, dealt with 4. Now I'm done, so now I can write down 1. Write down 1. Okay, that's cool. Now I'm done with 1. I roll it back to 3. Well, 3 is already finished with 0. It's already finished with 1. 4 is already marked, so I'm done with it. Now 3 is finally done. So now I write down 3. So this is my post-order traversal. So 0, 2, 4, 1, 3 is my post-order traversal of this graph. Now consider reversing it. 3, 1, 4, 2, 0. Is this a topological sort of our graph? Well, let's check. So I do 3 first. That's good because, hey, 3 doesn't have any dependencies, right? So that one I can definitely do. Then I go to 1. Well, 1 only has one dependency, which is 3, but that's already done, so that's good as well, right? So 3 is good, 1's good. Now I like to look at 4. 4 depends both on 1 and 3, but oh, hey, those are the things we just finished. So 4 is good to go as well. Now I finished 4, right? And my other two choices are basically 2 and 0. And while here it says 2, well, 2 is good to go, right? Because we did 1, we just did 4. 2 is good to go. Last one is 0. 0 requires 3 and 1. We already did those, so we're done. So yeah, this reverse post order here is a topological sort for our graph. Okay, so this is, we're not having to invent a completely new algorithm for topological sort. We kind of already have it. Okay, so this is a very nice thing. All right, so that's all I got for this video. All right, so we've kind of traced it. We've seen that we produce a topological sort. In the next video, we'll give a little bit more reasoning for why it's a topological sort, and also what to do when you have more complex complex graphs. Because sometimes one thing that we get into trouble is that if we have maybe a bad choice for where to start. This example just happened to work out because we started at 3 and everything was reachable from 3. But if we had started at, for example, a node like 0, well, then we wouldn't have been done, right? So how do we pick our starting position? So anyways, in the next video, we'll kind of elaborate on this, right? For now, we've at least discovered one way to get the topological sort of a graph.